The year is 2015. I'm dressed in full military fatigues, sitting in a humid jungle, not unlike this one. Before I started as a machine learning engineer, I did a stint in the army. And every so often, we'd have to go for exercises. And you would be given a status monitor that looks something similar to this. And what it does is that it shows you your simulated healthiness and ability to fight. So for example, over here, it's showing that there's a simulated minor laceration. And the important bit is below, where it's saying that I can still walk and shoot. But if any of these said N instead of a Y, that would mean that my simulated injury was preventing me from either being able to walk or to hold my weapon. So as I'm sitting in the jungle, a simulated artillery strike goes off, and the status monitor starts beeping. I pull it out, and I see that I have one of the strangest injuries ever. It says, fragment un, left buttock. And then right below it, walk yes, shoot no. Now this doesn't make any sense at all because they literally just told me that my leg got impaled by shrapnel. It would have made more sense if they told me walk no, shoot yes, unless I'm some sort of strange being that goes around walking on my hands and shooting with my feet. But this brings us to a very important point, which is that things need to make sense. There are certain rules that we expect the world to follow. And this is a problem for us here at Nearmap because we have an AI product, and sometimes it runs into rule violations. So this is an image of a roof. We have asked the AI to basically predict these three classes. And as you can see, we have predicted that there's rusting on the roof as indicated in red, but we have also indicated that it's not a metal roof at all. This is the story of how we built Nearmap's first ontology system to properly improve how we store and capture the relationships between the classes that our AI predicts on, and to use insights from those relationships to improve how we train our AI. In this story, we'll be talking about a broken system that we looked at, and we asked, what are the requirements we need in order to make this work? We'll talk about the obstacles that we met along the way and how we solved them. And we're going to finish our story with how we did a POC last year and the benefits that we're seeing from it. So our story begins with Nearmap. Who are we? We started out in Perth in 2007, capturing aerial imagery as a sort of higher resolution and more up-to-date Google Maps. By our fourth year, we were publishing 184 flight maps per year. Right now, we're doing thrice that number. And then another 4 years after that, we expanded to the US. But this whole time, we had just been selling photo maps. But that changed in 2017 when we released an upgraded camera system capable of producing 3D content, and together with it, digital surface models, and what we call true ortho imagery, which is corrected for parallax error. It solves a building lean issue that you tend to see in normal aerial imagery. And then this is the bit where we come in. 2 years ago, Nearmap AI was launched. Since then, we have grown from 34 classes that we train and predict on, with a training data set of 204,000 labeled images covering an area of 1,500 square kilometers, to 78 classes, and a training data set 3.5 times as large. Nearmap's AI is a supervised semantic segmentation model, so that means, firstly, that we rely on large amounts of human-labeled data in order to train our AI model, and secondly, that our labels consist of some sort of indication of what pixels belong to what class. So properly communicating these definitions of the classes to our labelers is essential to making this work. So what you're seeing on the right is a visualization of a roof label. So there's an image of a roof, and what I've done is I've overlaid it with the yellow pixels indicating where there is roof, and the greenish pixels basically indicate where there is no roof. And I have it here to point out two things. Firstly, defining the edges of objects can be tricky. So if you look here, this is a relatively simple case where the roof isn't straight, it's slanted, and you can't represent the label by a single neat row of pixels. So the pixels basically go roof, 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 and then in the same row, not roof, not roof, not roof, not roof. And the way you define your class should be quite explicit about when a pixel is that class or when it isn't. So essentially where that step that you're seeing should occur. The other thing that I'd like to point out is that if you look at this part of the image, the label basically forms a straight line, even though there's vegetation obscuring our view of the roof. And this is something that we explicitly asked our labelers to do, and it's something you may want to account for in your definition about where line of sight comes in. So I joined the team just before the Gen 1 AI product came out. I actually graduated with a degree in aeronautical engineering, and I got my introduction to AI in 2016, training neural networks to recognize handwritten digits on the MNIST dataset. Since joining, I've worked on 4 separate projects, including a verification module that performs heuristic checks on our training data, and the ontology system that we'll be talking about today. Meanwhile, Anne is our ontologist. She's completed a master's in library and information science, and prior to joining, she's worked on definitions for master data management, semantic data management, and model-based systems engineering for risk. So she's the one who designed the ontology itself, and she'll be talking us through what the existing system was like, as well as the first 3 obstacles that we faced.
Great. Thank you, Zeph. Okay, so I joined Nearmap, and this was the current state of the label class definitions. It was a wiki. And so you'll notice here the definitions were stored as text. That meant to share them between our other systems internally, we had to copy and paste, very high tech. They included inclusions and exclusions and example images, also labeling instructions. All of those things were inconsistently applied, to say the least. Each layer has between 10 and 150 sample images. And so with inconsistent metadata, how can you say that those images actually represent what is in the real world? So this is what I had to start with, and so I worked with Zeph across a 16-hour time difference, because I was still in the States at the time, to come up with a solution. And so some early decisions we came up with were the use of Protege, which is an open source ontology editing tool, and the tool I was most familiar with. I have to get this right because I see the Neo4j folks in the back of the room. Protege ontologies are serialized in OWL format. And Neo4j has the built-in ability to import RDF XML files without us having to parse them ourselves. In addition, the Neo4j's Cypher query syntax provides more future-proofing than Sparkle, as Cypher enables querying variable length paths, meaning we're setting ourselves up well for complicated graph walks in the future. Because as Zeph was saying, we have about 78 layers right now, but what happens when we get to 1,000? How do we manage it then? It's a very different question that we wanted to make sure we future-proofed some of our solution. And then we use GitHub for all of its versioning and branching and file storage. So the key components, the ontology, like I said, gets serialized to an OWL file, which we commit to the working Git branch. When we push the commit, a Circle CI job extracts the information we know will be commonly accessed and passes it over to our backend API. The API sits on top of an RDS instance and updates it if the data is valid. If the data is not valid, it can fail the job by setting an HTTP error code. If the job passes, we also publish the definitions as a static site for consumption by team members and downstream apps. So we've already solved the copy-paste problem for a few systems. So the first challenge, as I mentioned, was scaling the ontology. We have 78 classes right now, planning on going to a lot more. So how do we design for the future when the future is uncertain? And I say a lot, but what is an ontology? In its simplest form, it is a set of rules about a domain in the world. And that can be also used to manage metadata. So it's a set of rules, can be used to manage metadata, a little bit of logic about the world. So we had some challenges when coming up with the ontology. Had some idea, the first thing you do when you define an ontology is you think, okay, what is the domain that we care about? And what is the level of abstraction of that domain that we want to model and create rules for? And so we decided that the domain at Nearmap is a little area called the livable world, which is a very significant system of systems. And so to scale that back for this first effort, we decided to focus on, the livable world, so not large natural areas, but mostly the built and human-manipulated environment. And so with that, we wanted to make sure that our livable world objects and concepts were separate from AI constructs such as line of sight. We wanted to be able to manage those separately. Also needed to be able to capture the nuance of Nearmap logic. What does the real world really look like, and how do we capture that? Also honor our definitions and what they currently say. What is a line? And the best practice in the ontology world is don't build a monolith. You don't want to build this large, unwieldy structure that only I understand, so that when I go on vacation and someone else tries to figure it out, they have no idea what I was thinking. So with those guidances, try to work on the next thing. So after you figure out where your domain is, what you need to do, you try to think about, okay, should I borrow or build? It's a common question. So I was really, really excited because I found this environment, Ontology, and it had our entire scope. I was like, oh my God, my job is so easy. Until I looked at one of our core classes, what is a building? And when you think about a building, a lot of us, in this learn to draw example, think of something with walls and a roof, and it's a box. But at Nearmap, we capture the real world. We captured all its nuance and complexity and beauty. And there are times when a building will never have a roof or does not have a roof, but it is still a building. Sometimes it might even have full walls, so under construction, it's gonna have a roof, doesn't yet, still a building. Sports stadium, technically does not have a roof, still a building. Tornado ripped through that area, took the roof off. That is still a building to our definitions. So my dreams were crushed. I could not use the environment Ontology. So I got to build the Ontology largely from scratch, which was actually really awesome. And so I tried to get a little fancy with my relationship development and wanted to do some Boolean logic at the front of my nodes and edges. And I did this, and you try to put two things in the front, but that creates what's known as a collection in the Ontology, which if this was not having to fit into Zeph's system, would be fine. But because we're trying to put it in Neo4j, when you create a collection, that creates a blank node in Neo4j. And so I had to scale that back and stick to the more traditional and structured class, relationship class structure in my relationship. So that was one of my big learnings. And so the solution was a custom metadata schema where I was able to leverage some of the SKOS or SKOS upper level ontology for some of our required metadata fields. I came up with a set of 16 reusable relationships that are domain agnostic, so we can use them across any of our domains in any part of our ontology. So when I say ontology, it's actually 5 different ontologies that are layered like a cake that you can use and interoperate with each other, because we wanted to manage different things separately in different spaces, but then also bring them together in a file to manipulate them and create the logic and add the relationships. So the relationships are managed separately from the objects, and the AI concepts are managed separately from the livable world objects, but then they all come together in a big happy ontology. So I said a lot about metadata. What about our images? We're known for being an aerial image company with a little bit of AI thrown in. So where do you see the images? Why aren't they in the ontology? Well, as you said, aerial imagery is how we convey the truth about our livable world. And as I said before, every single layer has between 10 and 150 sample images that represent what that layer actually is. So we thought, oh great, we can just add the images in Protégé. Turns out you cannot. Well, short answer. But here's a question on Stack Overflow asking the same thing. So we explored this for a little while. You can add the images, but they get added as links or actual bytes, which has several disadvantages. It's bulky, bloats the ontology, and nearly doesn't fit with the concept of what an ontology is. It's not meant to manage things. It's meant to manage classes and representations of things. And so viewing a git diff of image links or bytes is apparently, according to Zeph, a nightmare. So didn't want to give Zeph nightmares. So again, we tried to use Web Protégé, which is the online version of Protégé, to see if we could get the images to show up in its changelog. But the main issue with this approach is that if you use this, you then lose all the branching and review goodness of Git. So why would we do that? And then there's the complication that images actually aren't really supported in the current version of Protégé anyway, so we just stopped this exploration and moved on to the next series of thinking. So our initial ideas, we also considered that didn't work, unfortunately. We were going to create this UI in the first screenshot that you see that would let us upload images to the ontology system. The images themselves would go to S3, while the links would be stored in a database. And then, to make sure we weren't uploading the same images twice, we'd have to be able to see the images currently associated with the class. So we need a display, like what you see in this center screenshot. And then for reviews, we'd need to generate a diff of the images added and removed based on what's in the database. We actually planned the diff report to be for the class details as well, which you can see in the third screen capture. So with all of this work, it became evident that image files themselves could not be included as ontology attributes in the OWL files. So how would we relate the images to ontology classes? The solution was to save images and their associated metadata in separate files in our repository, and by writing some code, pull all the information for each class into a markdown file, and let GitHub take care of the diffing. Which, yes, this means we have a folder called examples in Git where all of our images sit and metadata. The third challenge that we faced was the class development process. So labeling is really cyclical. There's no such thing as perfection, as much of a perfectionist as I am in definitions. You come up with a definition. When I'm convinced it's ready for the labelers, they are going to do some tests, get some sample images, label on that, come back to me. Once we review it, get all the edge cases ironed out, we send it to the model to be trained. Once the model is trained, we get those results back and review them, and then we make the determination if a layer is good enough to go to production or not. And so you can't wait for something to be perfect before releasing it. So we have to, think of all the edge cases, then you send it to the labelers, and we guarantee they're going to find you some edge cases you've never even considered. And so it's a very iterative process, and so we needed a way. It's a little bit of a chicken and egg problem. So we needed a way to be able to go through this entire process with the idea that a layer may never make it to production. It might end in sampling, it might end even before we get to the labelers, it might end when the labelers come back to us and say this doesn't work. The easiest thing to do is you just change a couple words in definition, and the hardest thing to do is you have to change the class completely. And so our solution for branching was to mirror our labeling environment, which has both live and training branches. The training branch is where we started to put things out to. And so that's where we know that it's going to be throwaway because it's mostly for training and learning. And then if it's good enough, a definition and a layer can get promoted to the live branch after another series of reviews. And so, as I mentioned before, the simplest change can be changing just a word or an image, but the most challenging thing would be how are we going to version this thing? So turn it back over to Zeph.
Yep. So for versioning, there were a few things we had to solve. For compatibility with the old system was assigning integers as IDs for each of our classes. So we had to keep on doing that in order to not break the old system. We had to make sure that we didn't assign an ID that already belonged to an existing class to a new class, and that had to happen even if we were creating 5 different classes and 5 different branches at the same time. Protege also wasn't that much of a help with it because they had a completely different concept of IDs. So basically the way Protege handles IDing is that they will want to have a URI for each of your classes in your ontology, not an integer. We also had to decide when we wanted to bump versions. So I have this really nice screenshot here where the diff is basically just a missing space being added in. So do we want to bump versions for that? If I ask Anne to make the judgment calls on when to bump versions, what if we thought a change wasn't significant and we didn't bump the version, and then it turned out to be significant and then the version wasn't bumped? Or maybe we could get the versions to be bumped in an automated fashion, but then how do you prevent your versions from fragmenting? So with this example of the missing space, you have a lot more examples like it. You have things like spelling errors, changes from active to passive voice, differences between American and Australian English. Is it a gas station or a petrol station? So normally with an automated system, you could hash certain details in your class, but all of those errors are going into your hash. You're going to get fragmented versions. And then finally, how do you deal with edge cases? When you encounter one, is it going to be a version bump, or is it going to be a completely different class? As one of my colleagues said, some corners are larger than others. So the 2 existing solutions for ontological versioning were graph versioning and temporal versioning, and neither of them worked for us. So with graph versioning, you have the one graph, and every time you make an update, that's a new graph entirely, and each of these graphs has a version attached to it. So what that means is that you're going to have a lot of classes which have all these multiple versions, but they're actually consistent across different classes because we didn't make any updates to them. Temporal versioning, on the other hand, splits a class from its data. So you have one node for the class, and then you have the details in another node, and you join them together with, in this case, it's a has class details relationship, and that relationship has timestamps on it. And then when you want to make an update, what you do is you create a new class details node, and then you update the timestamp so that the old relationship is out of date, and the new relationship becomes the current one. The problem with this is that it's a much more complicated procedure. You're a lot more likely to get the search and update queries wrong. And there was this thing we wanted to do where we might signify that a child class has changed because its parent has changed. So if you wanted to do that in temporal versioning, you would set off a cascading series of updates. So what we did was to split our versioning into 4 areas, depending on what we wanted to track. We had the class itself, and this was defined by the URI in Protégé. But equivalently, you could say it was defined by the integer ID, which we still had to assign to it. Now, any change that was not dataset breaking, so in other words, a change that still allowed us to use the old dataset for training our AI, if we had a non-dataset breaking change, that would just be a version bump. But if we had a dataset breaking change, that would be a completely new version entirely. To capture things that were significant but weren't dataset breaking, we had the variation. And we had this as a semantic version. We didn't know if we needed this level of granularity, but we decided to just release it and see how it would get used. Now, these first two, the URI int ID and the variation, these are human assigned because, as mentioned earlier, it's very hard to algorithmically detect when changes are significant. But we also hash the class data to get the properties version, and this helps us fulfill the audit and traceability role. Now, by request from the team that was doing the downstream apps, the properties version does not include a hash of the example images or the labeling instructions that we include. So to track changes to those, you would have to rely on the update timestamps. Now, to catch human errors, we basically have a dry run job that we run on our draft branches. So we send over all the class details to the backend API. At this point in time, the payload contains the URI from Protégé, the int ID, and the variation that we've manually entered, as well as the properties version that we've hashed and the timestamp generated during the Circle CI job. And then the backend does a few checks. So if we have bumped the variation without any of the actual class data changing, it fails. If we are trying to assign a new class and integer ID that's already been assigned, it fails. So only when we get the HTTP 200 status back do we pass the job and allow the training branch to be the draft branch to be merged into training. And I'm proud to say that last month we formally deprecated the old wikis system. So there's a bunch of benefits that we are already seeing from this system. The one that the team is the most excited about is that we have integrated this into our labeling tool. So this is a screenshot of what the labeling tool looks like, and we basically have pulled the class names from our backend API. So anytime we rename a class, it will automatically get reflected in the tool. The auto-generated doc site that we mentioned earlier has also been integrated in. And we actually display all these instructions to the labelers right as they're doing the labeling for us. And we can make sure that the version of the instructions that they see matches the version of the data that's actually being produced. The other benefit that it's given us is data awareness. So what I mean by this is that data is noisy. It turns out that labelers often don't agree with each other, even if you're only labeling a single class. So this is a screenshot from one of our internal tools that we have. And we have basically asked 2 separate labelers to label the same image. And now zooming in, you can see a few pixels over here, which show where they actually disagreed. They gave different labels to the image. Now, this is just for one class or one image. So if you think about extending this to multiple different classes, you are going to get much larger conflicts. You know how your roof can have different materials? Well, we train our AI to detect that as well. So tile and shingle are 2 of the materials, and they are incompatible with each other. But because it's quite common to label different classes at different times, you can end up with different labelers labeling them, and those labelers don't know what the other person has labeled. And that's how you end up with situations like this, where basically we have one set of roofs, and it's got tile labels on it, that's the yellow, and it's also got shingle labels on it, which is the blue, even though those two are incompatible with each other. So we ran a POC with a simplified ontology, as well as running it on a reduced data set. And in that experiment, we detected ontological conflicts in 8% of the data. There's a bunch of other things that we'd like to do with the ontology as well. One of the things you can do is to create an embedding. So this example over here is a matrix where a 1 indicates that if one class is present, then another class must also be present. So more specifically, if you look at the first column, what it's telling you is that if any of the tile roof, shingle roof, or metal roof classes are present, then you know that that same pixel is also a roof. The zeros represent classes which are mutually exclusive. So now onto the second column, you know that if there's a shingle roof label there, then it cannot be a metal roof label. Sorry, if it's a tile roof label there, you know it cannot be. Sorry, okay, let me do this properly. So the rows are the ones which indicate what is there, and the columns tell you what the implied conclusion is. So the second column is telling you that if you have a shingle roof, it cannot be a tile roof. That's the 0 in the third row and second column. So I got it right this time. And then it's also telling you that if you have a metal roof, then you cannot have a tile roof. So that's fourth row and second column. And what we are doing is we're building custom loss functions to directly penalize our AI for violating these rules. And we're hoping that by doing this, we can produce predictions which are more in line with real-world expectations. So our AI product is only going to continue to grow. And as that happens, that means many more classes are going to be added and many more relationships. We hope that this shift from wikis to the ontology system will help make managing all these definitions easier and hopefully just cut down the number of fragment und left buttock scenarios. Thank you.
How do you guys deal with compositional data? So like your roof is made of multiple parts, and do you do multi-label prediction or?
Yeah, so we allow a pixel to be multiple different classes at the same time. When it comes to roof material, we specifically made our definitions as well, such that the different materials are mutually exclusive. But like, for example, in the with the vegetation example that I showed earlier, that pixel would have been labeled as both like vegetation and roof at the same time.
Right. When you're designing the ontology, how do you incorporate compositionality into it? Like a building is made out of walls and
yes,
roofs and...
I segmented it as parts, so you can kind of think of it like Legos. So everything is not like, it's kind of that wall and wall, roof equals building. It doesn't have to equal a building. It can be that each of those pieces are things that exist, and when you combine them, they can be considered parts of a bigger thing.
Do they go back into the constraints that in your custom loss function then, when you add more parts that you can compose together?
That's a really good question.
Wait, so you're asking about the loss function, right? Okay, so with the loss function, it's something that we're still working on. We don't really have a clear picture of what it will look like. We're still testing it out on like a simplified version, so we haven't gone to such complicated lengths yet.
That's one of our next steps.
Hi, using the roofing example, for residential houses, what about solar panels? How does it help? Or does it get in the way for determining what kind of roofing you have?
Solar panels are roof objects. So again, they are a thing that exists in the world, and then they can have a location that can be the ground or the roof. We haven't started putting location logic in the ontology yet. That's kind of phase 2. First phase was kind of just define what objects are and kind of identify those like 16 kind of core relationships, but location starts to get to a whole other world of complexity that we're going to tackle in the future.
I love this idea of the ontology for structured labeling and having relationships and testing the validity of the results of your models. It's amazing. I'm just curious, the role of Neo4j Is it just for storing your ontology and working with it as you're defining it, or do you use it for more?
So the idea is that by doing a graph walk on Neo4j, we should be able to automatically produce the embedding. That was the original reason why we were looking into it. But the second reason is also that essentially the use of Protege locks us into the OWL file format, and instead of having to write our own parsing logic, it's quite simple to just import it into Neo4j and just pull the class data from there.
Please, thank you, Anne and Zeph.